Now that we know a little bit about how to write chemical reactions, we can start to study the quantitative relationships in those chemical reactions. Remember that the word quantitative means measurable, so there are measurable relationships that exist between the reactants and the products in chemical reactions. It's sort of like comparing the amount of ingredients needed to make a recipe. In order to do stoichiometry, you must have a balanced chemical equation. The equations must be balanced so that we know how much of each reactant and how much of each product are present. This is similar to a recipe. A list of ingredients is not helpful when doing a recipe unless you know how much of each ingredient you need. And in a recipe, you might have measurements like teaspoons or cups or ounces. And in chemistry, the coefficients in the balanced chemical equation always represent the number of moles that are needed for the reaction to occur, or the number of moles that are produced by the chemical reaction. When looking at a chemical reaction, you can create conversion factors that relates the amounts in moles of any two substances that are involved in the chemical reaction. So for example, the ratio between aluminum oxide and aluminum is a 2:4 ratio, whereas the ratio between aluminum oxide and oxygen is a 2:3 ratio. When we write mole ratios, we often write them as fractions. Notice for the relationship between aluminum oxide and aluminum, we can either say it's a 4:2 ratio with 4 moles of aluminum on top and 2 moles of aluminum oxide on bottom, or we can take that conversion factor and flip it upside down and say there are 2 moles of aluminum oxide over 4 moles of aluminum. And which conversion factor we use depends on which chemical we're starting with versus what chemical we are solving for. Remember from Chapter 3 that we created a mole map, which acted like a flowchart to allow us to convert between different units of the same substance. In stoichiometry, we can expand on this mole map to allow us to convert between different units of different substances. So we're going to take this old mole map and make a mirror image of it to create a new mole map. Notice on the left-hand side is our old mole map, but everything is labeled substance A. And everything on the right is the mirror image with the substances labeled B. The substance or chemical that is labeled A is always going to be the substance in which the value is given to you, whereas substance B is always the unknown chemical that you're solving for. In order to learn how to use this new flowchart, you simply need to practice a number of different stoichiometry problems. And so I will work through 4 examples with you that show the 4 different types of problems you're most likely to encounter when doing stoichiometry. The first type of problem is a simple mole-to-mole conversion, where you are converting from moles of one substance to moles of another. Ammonia is widely used as a fertilizer and is found in many household cleaners. How many moles of ammonia are produced when 6 moles of hydrogen gas react with an excess of nitrogen gas? In order to solve any stoichiometry problem, you must begin with a balanced chemical equation. So you'll first need to write the chemical reaction showing hydrogen and nitrogen combining together to make ammonia, and then balance it. You should get nitrogen plus 3 hydrogens yields 2 ammonias. And once you have the balanced chemical reaction, you can then use the mole ratio between hydrogen and ammonia in order to solve the problem. Just like we did when we solved mole conversions earlier in the year, we're going to start with the value that is given. So in this problem, 6 moles of hydrogen gas is given. And then we're going to create a T-chart in which we write whatever we can solve for on the top. If you look back to the revised mole map, you'll see that from moles of one substance, we can now convert to moles of another substance. So I can write moles of ammonia on the top. Remember, the units that go on the bottom are those that are required in order to cancel out. So this would be moles of hydrogen. And now we have a mole ratio that will need to go here. That mole ratio depends on the coefficients that are in the balanced chemical equation. So since there's a 3 before the hydrogen and a 2 before the ammonia, I write those numbers in my T-chart. Since all I want to solve for is moles of ammonia, I can stop here. And I'm going to multiply across the top, and then multiply across the bottom, and divide those 2 numbers to get my final answer. So my final answer will be 4 moles of ammonia. The second type of problem takes the mole ratio one step farther, where you're starting with the moles of one substance and solving for the grams of a different substance. What mass of glucose can be produced from a photosynthesis reaction that occurs using 10 moles of carbon dioxide? Again, you have to start with a balanced chemical equation anytime you're doing stoichiometry. So the photosynthesis equation is 6 carbon dioxides plus 6 waters yields glucose and 6 oxygens. To start this problem, I'll start with the value that is given to me, which is 10 moles of carbon dioxide. And then I can look at my mole map to figure out how many different boxes I'll need for this conversion. So moles of carbon dioxide will be the same as moles of substance A. And I can go from moles of substance A to moles of substance B, which in this case is my glucose. And then once I'm in moles of substance B, I can then solve for grams of glucose in the last box. So the tops of the boxes should match the squares on your mole map. In the bottoms of the boxes, we write the units that we need in order to cancel out. So moles of carbon dioxide will cancel out diagonally, and moles of glucose will cancel out diagonally. And then you can just simply plug in your numbers. So when you have the 2 moles stacked on top of each other, that is your mole ratio, and those come from the coefficients in the balanced chemical equation. So there is a 6 before the carbon dioxide, and there is a 1 before the glucose. In the last box, anytime I'm converting between grams and moles, I need the molar mass. And in this case, I'll need the molar mass of glucose. So I add up 6 carbons, 12 hydrogens, and 6 oxygens, and I get 180 grams per mole. And then multiply across the top to get 1800, and then divide by everything on the bottom, which in this case is 6. And 1800 divided by 6 is 300 grams of glucose. The third type of problem is simply the reverse of type 2, where we're going to start with grams of one substance, but solve for moles of a different substance. So oxygen was first discovered by Joseph Priestley in 1774. And he discovered oxygen by heating mercury oxide and causing it to decompose into its constituent elements. How many moles of mercury oxide are needed in order to produce 125 grams? Remember, you have to have a balanced chemical equation to start, so you'll want to write the chemical equation showing the decomposition of mercury oxide into mercury and oxygen, and then balance it. Your balanced chemical reaction should be 2 mercury oxides yields 2 mercuries plus oxygen. To set up my T-chart, I'm going to start with the value that is given to me. In this case, it's 125 grams of oxygen. And so this is the grams of substance A. From grams of substance A, I can go to moles of substance A, which is still going to be oxygen. And then I can go to moles of whatever I'm solving for. In this case is mercury oxide. So the top boxes match the squares on your mole map. The bottom units are whatever are needed in order to cancel out. So grams of oxygen and moles of oxygen. And then I can plug in my numbers. Anytime I'm converting between grams and moles, I need the molar mass of the substance. Since my chemical is oxygen, or O2, my molar mass is 32 grams per mole. And when you have the moles stacked on top of each other, you need the mole ratio from the balanced chemical equation. Again, those come from the coefficients. So there's a 1 before the oxygen, but a 2 before the mercury oxide. Take all the top numbers, multiply them across. So 250 divided by 32 gives me an answer of 7.81 moles of mercury oxide. The last type of problem that you'll encounter when doing stoichiometry is going from grams of one substance to grams of another substance. So when copper metal is added to silver nitrate in solution, silver metal and copper 2 nitrate are produced. What mass of silver is produced from 100 grams of copper? First, you'll need to write the reaction that represents this single displacement reaction, and then balance it. You should get copper plus 2 silver nitrates yields copper nitrate and 2 silvers. As we did with the other stoichiometry problems, we'll start with the value that is given and construct our T-chart. I'll begin by writing 100 grams of copper. 100 grams of copper is like substance A on your T-chart. So from grams of A, I can go to moles of A, which in this case will be moles of copper. And then I can switch substances and solve for substance B, which in this case will be moles of silver. And then from moles of silver, I can solve for grams of silver. The units on the bottom will be whatever are needed to cancel out. So grams of copper, moles of copper, and moles of silver. And now I just plug in my numbers. Whenever I'm converting between grams and moles, I need the molar mass of the substance, which in this case is copper. So 63.55 grams of copper per mole. When I've got the two moles stacked on top of each other, I need the mole ratio, which comes from the coefficients. So there's a 2 before the silver and a 1 before the copper. And then here, converting between grams and moles of silver, I'll need the molar mass of silver, which is 107.87 grams per mole. In your calculator, you'll take all of the top numbers and multiply them together, and then divide by all of the bottom numbers multiplied together. And if you plug these into your calculator correctly, you should get an answer of 339 grams of silver.